Hello everyone. Well, today I want to show you a little bit about induction motors, and I want to share a few basic principles and a few basic electrical formulas, nothing too complicated. And I'm going to show you a couple of tips and tricks and ways that you can run this induction motor, and any induction motor really, any way you want. I'll show you how to get more torque out of these things and more speed out of these things. But before we begin, I want to say, just prepare yourself. There will be a couple of formulas, and I might not explain them in the best way that everybody can understand. I just explain it in the best way that I know. So, let's get started. Okay, one of the first things I'm going to explain is basic things like electromagnets and electromagnetism. So, most people who know anything about electricity know what one of these is, or what it's supposed to be. The simple piece of iron with a wire wrapped around it is usually called an electromagnet. And what it does is one of the most basic electrical things. So we got a little piece of metal here, and we have a battery and an electromagnet. And when we apply power to it, it becomes magnetic. Because whenever there's an electric current flowing, there's a magnetic field created. And when we coil the wire around an iron core, it concentrates that magnetic field. So we get an increased magnetic effect when we apply power to the electromagnet, and the piece of metal is then strongly attracted to it. Now, when we look at the actual induction motor, like one of these induction motors, we notice that the induction motor is actually made up of many electromagnets, quite a few of them. And the number of electromagnets is dependent on the physical size and the number of poles or pole pairs inside of the induction motor. Now, the basis of the operation of the induction motor is pretty simple, but before I get into that, we need to examine the electromagnet and the operation of that a little bit further. So, the operation, like I said earlier, is quite simple. It just concentrates a magnetic field that is created when a current flows through a wire by coiling the wire onto an iron core, and that concentrates it. But the actual strength of the magnetic field is really a product, if you will. It's a product of the current that's flowing through it and the number of windings, the number of turns of that wire. So if we've got more turns and we've got more current, then we're going to get a stronger field. Or we could have fewer turns and a stronger current, and that would give us one size of field. Or we could have less current and more turns, and that would give us a similarly sized field. Now, one device that comes to mind when we talk about that would be a transformer, and that transformer does use the similar concept. So, for example, a step-up transformer, which increases the output voltage. The primary coil would have fewer turns, and the secondary would have more turns. Even though the field is the same strength, the magnetic field that transfers the energy inside is the same strength. And that's really one of the keys to the induction motor, especially if we want to get more torque out of it. Now back to the induction motor itself. The induction motor has two parts, the rotor and the stator. So let's separate them. This would be the stator core, and again, it's many electromagnets and many stacks of steel sheets. This is a rotor, which is usually aluminum, and has, again, stacks of it. Don't know if you can see those lines in there. Alright, but that's the rotor. And that entire assembly there would be the induction motor, and it would have a shaft moving through the middle of it. Now, the way it works is pretty simple. When an alternating current flows through the coil, it creates an alternating magnetic field, because again, the electromagnet coils concentrate that magnetic field. And whenever an alternating magnetic field is created, it will induce a current into any nearby conductor, which in this case would be the rotor. So it's inducing a secondary alternating current by way of a primary alternating current. So now there's two magnetic fields because the secondary current created a secondary magnetic field in that rotor. And those fields are always opposite of each other, so they interact with each other. And when they do that, they cause torque to be developed. Now, this is where it gets interesting with the induction motor. The torque is proportional to the strength of that magnetic field. So, if we want more torque, we strengthen the field. Now, earlier, I said that magnetic field is a function or a product of how many windings we've got, how many turns, and the current. So immediately you're thinking right away we should just increase the current. But if we have, say, a dual voltage motor and we use the higher voltage winding, then we can get more torque. Now, for example, on this motor right here, it says 220 or 440, and then it has two current readings. It's got like 3.2 amps and 1.6 amps. So we would want to use the higher voltage winding for more torque. And at that point, maybe you're thinking that doesn't make sense because the higher voltage winding gets less current. But remember, the field, the size of the magnetic field, or the strength of it, is really dependent on the current and the number of turns. Now, the higher voltage winding has got more turns on it. But you might be thinking, okay, that's got more turns, so that means it's going to have more back voltage, more voltage pushing back. So it will be harder for us to get current in. And that's true at 60 Hertz. See, that rating there is only for 60 Hertz. If we lower the frequency using a special little tool, the variable frequency drive, we can lower the frequency and push more current into those same number of windings. So therefore we're going to get a stronger field and we're going to get more torque. And again, I say at a lower frequency. If we increase the frequency, then we're going to get a weaker field. And to understand that, we have to go back to the electromagnet. Now back to the electromagnet. Now, I said if we increase the frequency and a number of windings, we're going to get a higher back voltage, and it's going to oppose current moving into it. So we want to lower the frequency to get a stronger field. And there's a simple explanation as to why it does that. So first of all, let's say we do not use the battery anymore on the electromagnet, and then we use alternating current. Then the electromagnet becomes what's called an inductor. Now, the inductor, as I said before, just like with the induction motor, produces a back voltage. The reason it does this is because the magnetic field that it develops influences the flow of current. So, if we apply an alternating current, the current's going to move one way and create a magnetic field. And when it reverses the other way, that magnetic field is still going to be there, and it's going to say, no, I don't want that current to reverse. So it's going to produce a back voltage. Now, there's a simple formula for calculating that back voltage, and it's easy. V equals L times di over dt. And I said before, there's going to be some formulas, and I'll try to explain this the best I can. Voltage of an inductor is equal to the inductance, or basically the number of turns, multiplied by the rate of current change, or the frequency. So immediately that says, if we increase the frequency or we increase the number of windings, there's going to be a greater back voltage that pushes back and inhibits the flow of current. So in the induction motor, when we use a higher voltage winding, there is a greater inductance, but with the variable frequency drive, we can lower the frequency and we can get more current over that same high number of turns. So therefore we get more torque. But as you can see, there is a flaw in that immediately, because with the variable frequency drive, if we increase the frequency, then we've got an increased frequency over an increased inductance, and that totally kills the torque at high speed and makes it not work anymore and basically stall. But there is a way that we can get greater speed out of the induction motor. Now we're back onto the induction motor, and you can see again the nameplate. It is rated for 220 and 440, or basically 240 and 480. And on 220 it says 3.2 amps. So basically for the same frequency we're getting twice the current. So immediately that says we're getting less of that back voltage, so the current isn't impeded as much. If we use the formula V equals L times di over dt, then we must come to the conclusion that we've got less L, or there's fewer number of turns in there. And if you're thinking about that in the actual induction motor, you're saying, okay, but it's still got the same number of turns. Well, the way it's wired, we can run those turns in series or in parallel, and when they're in low voltage, they're in parallel basically. So if we want to get a greater speed, then we'd use the lower voltage winding on a variable frequency drive that outputs the same voltage or a greater voltage. So to increase the speed of the induction motor, we want a greater frequency or a greater di over dt. But we don't want the current to be impeded, so we have to use as least inductance as possible. So when we are going to use that lower voltage winding, we can crank the induction motor up pretty high with the variable frequency drive. Now, there is one other trick that most variable frequency drives have up their sleeve, and that's a feature called torque boost. So if we're using a higher voltage winding on a dual voltage motor and we want to get more torque out of that, we can actually even lower the frequency and then increase the voltage higher than what it should be at low frequencies. And that gives us even more torque at low speeds, but then again, like I say, at high speed it does just about nothing. Well, that's enough talking for now, and now I want to show you, if I can, without this thing shaking and jumping all over the place. This is wired in 480 volts right now, or 440 according to this motor's nameplate, and I will show you how it works, where it tops out at, and then I'll stop, rewire it for 240, and then show you that it actually can spin a lot faster without the torque falling. So here it goes, and hopefully it won't shake all over the place. So at low frequencies you can really hear that rumbling the whole desk. It's got a lot of torque on it. It's got a lot of very strong magnetic field inside of it because it's going through all those long windings in the high voltage mode, and we've got increased voltage at a lower frequency, so we're going to get more torque. But as we speed it up, the torque falls. See, now we haven't got any more torque left at a high frequency. And the motor just slowly slows down until eventually it will stall. Right now, I'm going to rewire that motor, show you how much faster it can go. Alright, last time we got that up to about 200 Hertz and it quit. And I've rewired it for low voltage. Let's see what we get for some speed this time. Well, that one was about 350 Hertz. It's pretty good. see if we can try that again with me out of the way so you can see it. Well, it seems like that one tops out at about 350 hertz, but there is another way you can get more speed out of it. See, now that was a 240 volt motor on a 240 volt controller. So if we actually hooked that up to a 480 volt controller and wired it for 240, we could actually get even more speed out of it. Thing could just go stupid. Well, anyways, I hope you enjoyed this and I hope you learned something. If I didn't explain anything well enough or you didn't get anything, you're always welcome to ask me. See you next time.